Right, I'm going to have a go at recording this video about a section from Further Maths Core Pure 1, section 6.6 part 2, which is about solving systems of equations using matrices and, more importantly, interpreting these results geometrically. I think it's probably one of the trickiest sections in Core Pure 1, so this video will be quite detailed, will take you on a little bit of a journey and hopefully will make sense. If it doesn't, please let me know and I will re-explain sections of it. Right, first up, if we go to the PowerPoint, which starts here. A couple of key ideas to understand this topic. Firstly, it's about consistency of linear equations. It's an idea that we've come across before but might sort of jump at us out of the blue slightly when we are looking at this topic, because we're not expecting to be thinking about consistency while we are thinking about the geometric interpretation. So let's just read through. From Pure Year 1, you're already familiar with the idea that the solution of a system of two equations with two unknowns can be visualized by finding the point of intersection of two lines. A system of linear equations is known as consistent if there is at least one set of values that satisfies all the equations simultaneously. So we can think of that as at least one point of intersection. In 2 dimensions, that is at least one point of intersection of two lines. In 3 dimensions, it's at least one point of intersection of two lines, or in this situation, we're going to look at two planes. So, first set of equations we can look at is x plus 2y equals 1, 3x minus y equals 0. You could have solved that at GCSE, nice set of simultaneous equations. You would have found the solution to that in terms of x equals and y equals. You can think of this system of equations from a further maths point of view as 1, 2, 3 minus 1 times the vector xy equals the vector 1, 0. Right. If you want to check, you will find that 1, 2, 3 minus 1 is non-singular. That is, that the determinant is not equal to 0. That's key when we go into 3 dimensions. So, the determinant of this matrix, you can do a quick calculation if you like, is not equal to 0. That means that the system of equations we've got there has got a solution. If we look at this system of equations, x minus 3y equals 1, x minus 3y equals 2, we could plot those two lines and we'd find there is no solutions to that. The system of equations is inconsistent because there are no xy coordinates that satisfy both of these equations. It has no solutions. If you want to check, you could work out the determinant of this matrix, 1 minus 3, 1 minus 3, and you would find that it is 0. We say that matrix is singular. Final situation in 2 dimensions, we could have that x minus 3y equals 1 and 2x minus 6y equals 2. By inspection, you can see the second equation is a multiple of the first equation. That means these are both representing the same lines. So any xy coordinates on the first line also satisfy the second line. That means the system of equations is consistent, but it has infinitely many solutions, right? And you can see that the matrix 1 minus 3, this should say 2 minus 6, is singular. Okay, so there's a slight typo there, that should say 2 minus 6. And you would find that is singular, that is the determinant of that matrix is 0. We're going to look at what this means in 3 dimensions and in 3 variables now. Exactly the same ideas that we're going to have applied, but there are more complicated and more situations we can look at. Right, so scenario 1, the planes all meet at a single point. That means the system of equations is consistent and it has one solution. We're going to look at how to identify that from the matrices. Scenario 2, the planes form a sheaf. They have a line of intersection consisting of infinitely many points. The system of equations is consistent and there are infinitely many solutions. That shape there is known as a sheaf. You can think about it like the shape of a book that is turned open and all the pages come out of the central spine. Scenario 3, 3 planes could form a prism. The planes intersect in pairs, they don't all intersect at any one point, and that system of equations is therefore inconsistent. So there are no x, y, z coordinates that are going to satisfy all 3 of those equations that are going to be on all 3 of those planes. Scenario 4, 2 or more of the planes are parallel and non-identical. These are inconsistent as the parallel planes never intersect, and thus all equations can't be satisfied by one x, y, z coordinate. The way we're going to identify this is rows in the corresponding matrix which are multiples of each other will be parallel. So we're going to look at the matrix and see if there are 2 rows which are multiples of each other. Scenario 5, all 3 planes represented by the equations are equivalent. These system of equations are consistent. There are infinitely many solutions. So if we have got a picture in our head, we know what that means for the consistency of the equations and the number of solutions. The trick to this, or the skill at this part of further maths, is being able to identify which of those scenarios we're in given the matrix which represents the equations. To do this, we have to take a small swerve into the Cartesian equation of a plane, which comes from the vectors chapter of Core Pure. So we're going to put away the matrices chapter for now and jump into the vectors chapter. So just take this as read for now, that if I have a plane, the equation of that plane is some multiple of x plus some multiple of y plus some multiple of z equals a constant. Now the normal vector to that plane, which is shown on this diagram here, pi, capital Pi represents a plane, bold N represents a normal vector, is n1, n2 and n3, and you'll notice these are the coefficients of x, y and z. So the normal vector, that's the one sticking out of the plane at right angles to it, is easily found by looking at the coefficients of x, y and z. Notice the normal vector does not include the c. I'll explore why using GeoGebra in a second. Find the normal vector to the plane given by 3x plus 2y minus z equals 4. Pause the video for a second, read what I've said and see if you can spot the answer to that. Hopefully we have spotted the answer. Is the normal vector is 3, 2, minus 1. So the normal vector to that plane is 3, 2, minus 1. Another example, find the normal vector to the plane given by minus 6x minus 4y plus 2z equals 16. Give you a second to think about that. You'll have found the normal vector is minus 6 minus 4 minus a positive 2. If you're really paying attention here, you will notice that is minus 2 times the normal vector to this. So here we have 3 turns into minus 6, here we've got 2 turns into minus 4, here we've got minus 1 turns into 2. What do you notice about the 2 normal vectors? The second one is a scalar multiple of the first. That means the normal vectors are in the same direction. Are the 2 planes coincident? Well, they look like different planes. Let's bring it up in GeoGebra and see what these 2 planes look like. Right, here we are in GeoGebra with these 2 planes plotted. I'll just stick them up one at a time and we'll see what we get. Right, so the first plane here, 3x plus 2y minus z equals 4. You can see that plane, it's the blue plane there, the grey plane is the xy axis. So that is the first plane. The second plane, minus 6x minus 4y plus 2z equals 16, is shown there. And you can see the planes are not coincident, they are not representing the same plane, but you should hopefully notice these 2 planes are parallel. If I plot on the normal vector, 3 minus 2 minus 1, you will see that vector goes from the plane and is normal to the first plane. My second normal vector is there, you will see is in the same direction as the normal vector to the first plane. So that tells us what's happening here. Both planes have got the same normal vector, or one normal vector is a scalar multiple of the other, and therefore the two planes are parallel. Right. How do we go about checking one of these? Right. What would one of these questions look like? One of these questions would look like this. You'd be given a system of equations: 3x minus 2y minus 6z equals 4, x plus 3y plus 3z equals 1, and 3x minus y plus 3z equals minus 2. What I'm going to do with that is turn that into a matrix equation, which looks a bit like this. So 3 minus 2 minus 6, 1, 3, 3, 3 minus 1, 3, multiplied by x, y, z equals 4, 1, minus 2. You see, if I expand out those matrices on the left hand side, I will get to the equations on the left hand side here. What we can do is call this matrix A. If we call this matrix A, multiplying the left by A inverse, we know we can do that because we're already going to check that the determinant of A is not equal to 0. So we know it has an inverse. We can multiply on the left by A inverse. I've not shown that calculation here. You can just do that using your ClassWiz calculator. A inverse times A times x, y, z is obviously going to give us the identity matrix times x, y, z on the left. So multiply that out. It's just going to give you x, y, z. Multiply the 4, 1 minus 2 on the left by A inverse. Gives you A inverse times 4, 1 minus 2. Again, do that on your ClassWiz calculator. Gives you these 3 points here, sorry, this 1 point here, 3/7, 27/28 minus 65/84. That tells us that these three equations have got a unique solution, and moreover, we have found that unique solution. So we're in a lucky position here. If the question said interpret geometrically the solution, we would say the point that we have found is the intersection of the three planes. I'm going to show you what that looks like in GeoGebra, which is here. I'm going to put the three planes up one by one. The first plane is here. You can hopefully see that moving around. And I'm going to put my point, which I found, 3/7, 27/28 minus 65/84 on that plane there. And you can see that point is on that plane just down here at the bottom. I'm going to put equation 2 up now. Spin that round. You can see that point is also on plane 2. Put plane 3 up. Spin that round. Where am I going? You can hopefully see that point is also on plane 3. I'm going to put all three planes on at the same time. And you can hopefully see somewhere there that those 3 points, sorry, that point is on all three of those planes. Now, we were in a fortunate position there that the determinant of the matrix was not equal to 0. That means I could find the inverse. That means I could do this calculation, which I did through here. If the determinant of A is equal to 0, I'm in one of these four situations. I could be in a sheaf, I could be in a prism, I could be in two or more of the planes are parallel, or I could be in all three planes are coincident. So really understanding this means that we're going to be able to differentiate between all three of these scenarios. Let's see how to do that. If we found the determinant is equal to 0, we have to check if all three planes are the same or multiples of each other. That puts us in situation 5. Let's have a look at what that looks like in equations, then in GeoGebra, then I'm going to have a little summary box that tells us what to do. So 3 planes we could have: 3x minus 2y minus 6z equals 4, 9x minus 6y minus 18z equals 12, minus 1.5x plus y plus 3z equals minus 2. We can see by inspection here that if I take this equation and times it by 3, I get the second equation. If I take this equation and multiply it by -1/2, I get this equation. So by inspection I can see that all 3 planes are multiples of each other. And I'm going to look at what that looks like in GeoGebra now. So equation 1 gives me that plane there. Equation 2 gives me the same plane, and equation 3 gives me the same plane. Again, I can put all those on at the same time, 1, 2 and 3. I can see all 3 planes are coincident. Little task for you to do here now is if you show the determinant of matrix A equals 0, so the matrix A is going to be 3 minus 2 minus 6, 9 minus 6 minus 18, minus 1.5, 1, 3, and then find any set of coordinates that satisfy equation 1, and then plug those coordinates into equation 2 and 3. You will find those coordinates also, that coordinate also satisfies equation 2 and equation 3. If we didn't find that all 3 planes were coincident, what we have to do next is check that if 2 or more planes have the same normal vector. The situation we're going to look at is this: 3x plus 2y plus z equals 1, 6x plus 4y plus 2z equals 10, and x plus y plus z equals 1. We can see by inspection again that 3, 2, 1 multiplied by 2 is 6, 4, 2. So these two planes have got the same normal vector. Well, not the same normal vector, but they are a scalar multiple of each other. Let's look at what that looks like in GeoGebra. So if I put equation 1 on the screen there, x minus y plus z equals 10 is shown there. Equation 2 that's the wrong GeoGebra setup. Let's find the correct one. Here we go. So I have equation 1 and equation 2 on there. 3, 2, 1, 6, 4, 2. They're both on there. Same normal vector, parallel. Equation 3 is not parallel to those two and crosses through them. So to check if we're in this situation, we've got to first of all show the determinant of A equals 0. And show that a set of coordinates which satisfy equation 1 but does not satisfy equation 2, but they have the same normal vector. So what I'd like you to do is find any set of coordinates that satisfies equation 1 and plug those coordinates into equation 2, and you will find that they do not satisfy that equation. But you could just write a little explanation saying that the normal vector for equation 2 is 2 times the normal vector for equation 1, therefore those two planes are parallel, therefore we are in situation 4. Don't call it situation 4 in the exam, but explain geometrically that 2 of the planes are parallel and the third one crosses them. The next thing, if we find that is not the case, gets a little bit more involved again. I'm going to show you 2 situations. First one is that of a sheaf, the second one is that of a prism. If we eliminate z from equation 1 and 2 and eliminate z from equations 1 and 3, the The two remaining equations x and y will either be multiples of each other, therefore we're in a sheaf, or they'll be inconsistent, therefore a prism. So we can see what happens if we try and do that. So eliminate z from equations 1 and 2. Here's equation 1, 2 and 3. To eliminate z from equation 1 and 2, you've got equation 2 minus equation 1, which gives you x minus y equals 10. Next thing to do is eliminate z from equation 1 and 3. To do that, I'm going to do equation 3, take away equation 1, which gives me 5x minus 5y equals 50. Divide that by 5 gives me x minus y equals 10. You will see these are the same line. Because they are the same line, I know that I am in a sheaf situation here. I'm just going to click that through and show you what that looks like on Desmos. Here are my three equations, here are my three planes. You can see they all form a nice line there, and that line is the line x minus y equals 10. Coming back to this second one here now, if I started with this system of equations here, that x minus y plus z equals 10, 2x minus 2y plus z equals 20, and 6x minus 6y plus z equals 20, I could eliminate z from equations 1 and 2, gives me x minus y equals 10. Eliminate z from 1 and 3, gives me x minus y equals, 5x minus 5y equals 10. Simplify that, gives me x minus y equals 2. I can see again by inspection these are not the same line. Because these are not the same line, I know that my three planes must be forming a prism. Let's take a look at what that looks like in GeoGebra. So here's my three planes. Just have a look here. There's my first plane, my second plane. Obviously cross over a line because I've not got the same normal, and my third plane is there, and you can see if you look down the line those three planes form a prism. Now it's time for you to have a go at this, but before you do I'm going to try and do a very brief summary on my visualizer here. So trying to summarise this isn't easy because it's almost the understanding comes from the intuition and being able to visualise these geometrically. But I know some of you will want a solid set of notes you could take away saying, how do I do this? So let's think about that through. If the determinant of A is not equal to 0, that's good because it means we can find the inverse. That means the matrix is non-singular. Therefore there is one unique solution, and you can find it by multiplying on the left by A inverse. If the determinant of A is 0, then the matrix is singular, and we've got a problem of some kind. We haven't got one nice, easy, unique solution. So either it's consistent with infinitely many solutions, that means we're in a sheaf or in three coincident planes, or it's inconsistent, that means there are no solutions. That means we're either in a prism or two or more of the planes are parallel. To investigate if we're in a sheaf, if we're in three coincident planes, if we're in a prism, or if we're in two or more parallel planes, then we need to look at, first of all, at the normal vectors to the planes. And if two of the planes have got the same normal vector, we may be in this situation or this situation. If we're not, then we need to look at eliminating z from equation 1 and equation 2, eliminating z from equation 1 and equation 3, and that will tell us if we're in a sheaf or if we're in a prism. Time for you to have a go and test your understanding. The system of equations is consistent. Yes, good. And it has a single solution. Yes, good. Determine the possible values of k. Pause this for a second while you have a go at it. You've got to think about what does it mean for it to have a single solution, what does it mean for it to be consistent, what does that mean for the determinant of the matrix. Have a go and come back to me when you're done. Probably take 5-10 minutes on that. So if we have a look at the determinant of this matrix, we'll find that it is equal to k minus 15. You can't do that in your class whiz because you've got the variable k, but you can do that just by hand, and that is the situation they may ask you to in an exam. Have a solution require that k minus 15 is not equal to 0, therefore k is not equal to 15. Moving on. A system of equations is shown below. 3x minus ky minus 6z equals k, kx plus 3y plus 3z equals 2, and minus 3x minus y plus 3z equals minus 2. For each of the following values of k, determine whether the system of equations is consistent or inconsistent. If the system is consistent, determine whether there is a unique solution or an infinity of solutions. In each case, identify geometric configuration of the planes corresponding to each value of k. So there's a huge amount to do here. This is going to take you 20 minutes, half an hour to work through this question if you're going to do it properly. Pause it, have a go. I'll come back to you when you have had a good go. Assuming you have had a good go at that now, let's have a look first of all what k equals 0. Let's have a look what we should do, right? And then what that looks like geometrically. So k equals 0. We're just going to substitute k equals 0 into this. So we've got 3x minus 0y minus 6z equals 0, and so on. You're going to find that. You're going to find the determinant of that matrix. You're going to find this equal to minus 18. It's not 0, so there is a unique solution, i.e. the planes meet at a single point. So the system is consistent. There is a unique solution. And the geometric interpretation is the planes meet at a single point. Let's have a look at what that looks like in GeoGebra. K equals 0. Put all three planes on. You can see somewhere hidden in there, about here, all three planes do indeed meet at a single point. Next situation is looking at if k equals 1. So if k equals 1, again, all we're going to do is we're going to write out this system of equations with k equals 1 substituted in. When we've done that, we're going to first of all go through with k equals 1 substituted in and see what we find. We will first of all find when k equals 1 that the determinant of this matrix is equal to 0. We've then got to have a look at our three equations: 3 minus 1 minus 6, 1 3 3, minus 3 minus 1 3. It doesn't look like any of these have got the same normal vector, so we've not got three coincident planes, and we've not got two or more parallel planes. Therefore, if we eliminate z from equations 1 and 2, we're doing that by equation 1 plus twice equation 2 gives us 5x plus 5y equals 5. Eliminate z from, they've done equations 2 and 3, that's fine. I've always said 1 and 3, but you can eliminate z from 2 and 3 as well. That gives you 2 minus 3, which gives you 4x plus 4y equals 5. You can see that these two are both the line x plus y equals 1. So equation 4 and 5 are consistent, so the system is consistent, it has solutions and has an infinity of solutions, and all those solutions are on one line, x plus y equals 1, therefore the planes meet at a sheaf. Let's have a look at what that looks like in GeoGebra. K equals 1 looks like this. And you can see at k equals 1, all those planes meet on that same line, which you can see if you look down the barrel there. Final situation we've got to look at now is here. K equals minus 6. We're going to substitute in k equals minus 6 again. You're going to work through it with minus 6. You're going to first of all check the determinant of that matrix that you get. Presumably you're going to find it's not equal, it is equal to 0 again. Then you have to look geometrically what that means. If you've not done this yet, do pause it now and have a go. Coming back to you now, again we're substituting k equals minus 6. We're going to find the determinant is equal to 0. We're going to look at these two equations, 3, 6, minus 6, minus 6, 3, 3, and minus 3, minus 1, positive 3. I can't see any of these that have got the same normal vector. Multiply that by minus 2, multiply that by minus 2, no. Multiply that by minus 1, multiply that by minus 1, no. Half that, no. None of these have got the same normal vector. So again, I'm going to eliminate z from 1 and 3 by doing equation 1 plus... We've done this a slightly different way here. It's fine, you can eliminate whatever you like. What we've done here is we have eliminated x from equation 1 and 3 because it's easy to do because you've got 3x and minus 3x. That gives you 5y minus 3z equals minus 8. That means we've got to eliminate x from another pair of equations. I'm going to choose to do 1 and 2 because they've got a nice multiple of each other. So double equation 1 plus equation 2 is 15y minus 9z equals minus 10. These are different lines. You can see that if I was to divide this by 3, I'd get 5y minus 3z equals minus 10 thirds, which is a different line to that. Therefore, these systems are inconsistent. So the system is inconsistent and has no solutions, and the planes form a prism. Let's have a look in GeoGebra what that looks like. Putting k equal to minus 6 gives us this situation here, and then if you look down the barrel, I think we can see that these three planes form a prism. You can see it from that end, and we can see the prism from the other end just about there. There we go. Right, some exercises for you to try on this with some hints. It is a very tricky concept to get hold of, especially because we jump straight into normal vectors of planes which you haven't seen before. Do have a go at it, do work through that video a couple of times, take it slowly, do it with a pen and paper in your hand, do ask me if you've got questions.